Hello, welcome to your second video. This is number 2 about the chi-squared test for independence. Please watch video 1 if you haven't seen that one yet. Watch that one first. Alright, let's get rolling. As a reminder of something you saw in video 1, in statistics, and this is basically what statistics is all about, we have a population. We want to know something about the population, but maybe it is way too difficult to find out, get or gather data from the entire population. Therefore, we sample, get a small sample that represents the population, and based on what we can infer from the sample, we can make inferences about the whole population. So we run statistics on the sample, and we assume that those apply to everybody in the population. But to make that assumption, we have to make sure the sample is a well-taken sample, and also that the conclusions we're making are valid, and that's what this is all about. Let's continue. One investigation we were looking at in the first video was the idea of tossing a coin 10 times and seeing how many heads we get, and then using that to determine whether the coin is a fair coin or a biased coin. We talked about the idea of a null hypothesis and an alternate hypothesis, and in this case our null hypothesis was the coin is fair. In other words, probability of getting ahead is 0.5, and the alternate hypothesis, the coin is biased. The probability of getting ahead is not 0.5. We looked at significance levels. For example, to get 0 heads or 10 heads in 10 tosses was a very small percent, 0.195, or to get 0 or 1 heads or 9 or 10 heads, that was a 2.15% chance of that happening. So basically, by knowing these percent chances of these things happening, we can then say, all right, if that happens, that is enough to say then it's so unlikely that the coin must be unfair or biased. So that's the kind of discussion we had in the last video. Let's continue on now. So now we're going to talk about the chi-squared test for independence. This is a symbol often used for the chi-squared statistic. This statistic is specifically used to see if two variables are independent or dependent. That is why it's called the test for independence. So we have two variables, and we want to know if one variable affects the other one's outcome or not. All right, so we're testing for independence or dependence. That's the key here. Okay, an example we're going to use is racket sports. And the question is the choice of racket sport at a certain club independent of gender? In other words, do males or females tend to prefer one type of racket sport, or does gender have no influence? In other words, is there independence? There's no influence by gender on choice of racket sport. Let's check some data. So that question, and here's some data we have. So let's say somebody took a survey at their local club, and they took a survey of one male group, another male group, another male group, and then 3 female groups. And these are the choices made by all the members, what their favorite racket sport is. So we have all our raw data there. When we have raw data, it helps to put it in a form that is easier to see, and we'll do that in a minute in a table format. But for now, let's make a null hypothesis. So the null hypothesis is that preferred racket game is independent of gender. So in other words, we're going to assume, or we want to prove, that gender has no influence on choice of racket sports. So there is independence. So that's how we always begin a chi-squared test. We say the null hypothesis is independent. And therefore, the alternate hypothesis is that preferred racket game depends on gender. So again, always begin by saying independent is what we're trying to show, and then alternatively, if this doesn't work, we can then conclude that there is dependency there. Okay, so there's our data, and now let's take the data and put it in a more usable or easy to use form. So we're going to make a table like this, and we're going to call this the table of observed frequencies. Observed means from the experiment, from the sample, from the survey. It's the observations we have, and we call that F sub 0. Okay, so observed, there's not 0, O, sorry, F sub O, that's for the observed values. So here we have the sport on top, tennis, badminton, squash, and over here male, female. And we started the table for you with 10 here, because if you look at the 3 columns of male players and you count up how many say they prefer tennis, you would count 10 tennis people. All right, and the total of people here is 60, so I have that total there as well. So now your job is to fill in the rest of this table, and you probably won't need to get everyone here, because once you get a few of these, you can then get the others by looking at totals. But anyway, fill in the table, and let's see what you get. Okay, so again, these are called observed frequencies. So this table shows the obvious actual data we have from the survey, and these are the numbers you should have. Okay, so double check yours. We're going to use these numbers as we continue. Okay, so now we have that table of data. These are called our observed frequencies. Next questions are these. Calculate the probability a person chosen at random is male. So let's say we have this group now. What's the chance of selecting a male from this group? Okay, next. Calculate the probability a person chosen at random likes tennis. Okay, so how many prefer tennis? What would be that probability of selecting a tennis player? And finally, if these two probabilities are independent, find the probability that the person chosen at random is male and likes tennis best. So male person who likes tennis best. So here are the answers for those. Number one was, what's the chance it is a male? Well, we know we have a total here of 33 males out of the group of 60, so your probability of selecting a male is 33 out of 60. Likewise, for tennis, the total of tennis people who prefer tennis is 19, therefore 19 out of 60 is that probability. And finally, if they're independent, to find the probability of male person liking tennis, we just multiply the two probabilities. Okay, so male and tennis, we multiply and we get this probability here. Next, there are 60 people in total. So if the events are independent, find the expected number of males who like tennis. We know the number of males who like tennis is 10, but what would be the expected number? Because maybe this is not what would be expected from here. Okay, so if you remember, to calculate expected values, we take the probabilities. So the probability of a male tennis player, again, was what we calculated here. Multiply those, and then to get the expected value, we do that probability times our sample, 60, and that tells us 10.45. So even though in the real data, in the raw data, we had 10 males who prefer tennis, the expected number is actually 10.45. So we're close to the expected number, but this would be the expected number. So this is called an expected frequency, and we see it's F sub E. So we had F sub O for the observed values. Now we have a table of expected values. It's going to be the F sub E table, and I filled in the first value for there. So now do this second table and fill in the expected values in here. One thing you should know is when we make an expected value table, we keep the totals the same. We still say we have those 60 people, all these totals and all the columns and rows, we keep the same, and now it's just your job to fill in the expected values there. So try to find this next one here the same way we found this one. See if you can calculate badminton there. Okay, so here are the expected values. Badminton was 11, and that one you can get by doing the probability of getting a badminton player times the probability of it being a male, and then times 60, and that's what would give you the 11 there. And check your other numbers as well. Okay, so note the expected frequencies. This is a rule for when we do this kind of test. The expected frequencies must be greater than 5. Notice all our values here are greater than 5, so this data is valid for continuing with some analysis. If you ever saw an expected value there less than 5, maybe your sample is too small, or maybe you need to combine some of these columns or rows into another single one so that the numbers grow. That's important to remember. Okay, so now let's talk about something called degrees of freedom. So we had that table again, we had our totals here. And the question is, when you were finding the expected values, did you need to find all 6 of these expected values by doing that probability times 60 calculation? Or could you have found a smaller number of these and then used the totals to help you fill in the rest? So what is the smallest number of these 6 spaces that you could have calculated and then been able to figure out the rest using the totals? All right, I hope you did some logical thinking there and thought of, well, 2. So let's say we calculated this value and this value, which we had 10.45 and 11, and now you can stop. You don't need to calculate the rest using that formula, because now that you have 2 here and you have a total of 33 here, you can do 33 minus those 2 and get this one, right? And then once you have this one, you can do 21 minus that one to get this one. And all of a sudden, you can do the same thing here. You can do 20 minus this one to get this one. So all the other boxes can be filled in if you just had these 2 to start. So the answer is 2. And we can look at that as 1, this row here, 1 row, and 2 columns. So I did 1 times 2. And the reason we have those, you'll see for next step here. So if your table had 3 rows and 3 columns, imagine this was, instead of 2 rows, it was 3 rows and 3 columns, which it does have 3 columns, then what would be the smallest numbers of these that you would have to calculate in order to fill in the rest like we did here? Well, hopefully this time you're thinking 2 times 2, which is 4. And there's a pattern emerging here. Basically, look, when we had 2 rows, we had a 1 here. And when we had 3 columns, we had a 2. Okay, and now we're saying, what if it was 3 by 3? So if there's 1, 2, 3, then you would have to have 2 and 2. So think about those numbers, because the next question is, what if you had 3 rows and 4 columns? Well, that number is 6. Okay, 3 rows, 4 columns. So what connection do you see between these numbers and what we're saying here in terms of the table? 3 rows, 4 columns, okay? So find the smallest number of entries in the table that had n rows and m columns. Actually, let's make it, instead of n and m, make it r rows and c columns. Okay, the answer for that is this. So the pattern you should have noticed here is every time you have a certain number of rows and columns, to get that number of minimum things that have to be calculated, you just take 1 less than the number of rows times 1 less than the number of columns, and that's what this is showing here. So for example here, we had 2 rows, but we took 1, and we had 3 columns, but we took 2. So it's always 1 less than the number we have, and you multiply those to get that least number. That, what we just looked at, is called a degree of freedom. And what does this number of degrees of freedom represent? Well, let's take a look at this. What does this mean? Basically, the number is called the degrees of freedom, often written in this form of V. This is because you only have a free choice for the numbers that go into that many cells. So in this case, our free choice was 2 that we calculate there, and the rest of the cells have to be filled in based on these totals. So these are our freebies, and then the rest are filled in based on the totals. So that's what degrees of freedom means. That number is going to become more important later. You'll see how. Okay, so the formula is rows minus 1 times columns minus 1, and that's what we just talked about. We'll take a look at that more next time. Okay, so now if we want to decide whether 2 variables are likely to be independent, it is necessary to compare the observed values with the expected values. Okay, so we had our observed values, the actual data. We had our expected values when we did the calculation using probabilities. And then if you compare them, you can basically say, is gender independent of, or is sports choice independent of gender? Because if these numbers, the expected values, if our observed values are way different than the expected ones, then we can say, oh wow, then gender must have some influence, because we're getting much different results than what is actually expected. Okay, so keep that in mind there. That's very important. So again, so how do you measure how far away they are? If we said, okay, we're saying, okay, there's a big difference between observed and expected values, we can say that there's some kind of dependence here. Well, but what is far away? How far apart do the values have to be? Like I see 7 here and 11. Well, those seem pretty far apart. Or 16 and 11.5. Those seem like there's a big spread between observed and expected. But how much is enough? That's the question. There is a way to calculate that. It is called the chi-squared statistic, and that's what this video is all about. Here's the formula. The formula looks like this. Let me explain it. So the formula works like this. You have that formula. What you do is you take your observed value minus expected value. So for example, 10 minus 10.45. And then you square it. And then you divide by expected value again, so 10.45. So it's like saying how far is this one from this one, and then divide by that one. All right, and then you add the next one, 11, observed. Yeah, is that observed? Oh, I wrote it the wrong way, didn't I? Let me change that, 1 second. Okay, here we go. Let's try again. I made the fix there. So observed minus expected over expected, and these ones here are squared. So this symbol here, as you may remember, is letter sigma, Greek letter sigma. It means the sum. So you're doing that thing plus the next one plus the next one. So you're going to do that for every single one of these values, except for the totals. You don't do the totals. You only do these 6 here, right? So do that calculation. Actually go through the steps there, add all those up, and see what you get. That value you get is called the chi-squared statistic, and that number will help us to determine if there is a relationship between the 2 variables. Does gender actually affect choice of racket sport? And we'll look at those details next time, but for now, just know you need to be able to calculate the chi-squared statistic. So what is it? What do you get for it here? Well, in this case, our chi-squared calculated statistic is 7.09. We'll look at how to use that next time, but there's the value here.